In this section, we're going to look at the natural exponential function, and we'll start off by looking at the number e. Now, if you recall from before, e is an irrational number like pi. The digits go on forever, never stop. The number e pops up quite a bit in applications like investment and statistics. So it gets its own special name, and if you punch it into your calculator, you'll see that e is got those digits and it goes on forever and ever. The number can't be put as a fraction because it is irrational. And if we look at the limit analysis of this expression 1 plus 1 over n, and we make n large go to infinity, we approach this number e. This is something you'll study in calculus when you actually take the limit of expressions. For now, we're just going to look at our TI calculator, put that expression in, and use the table feature to get an idea of as n gets big, how that expression turns into basically something like close to 2.718, blah, blah, blah. So let's go pop up our calculator. So I have that expression 1 plus 1 over n raised to the n input into the calculator using x for n, of course, and I'm not interested in the graph of this. I mean, I can look at the graph and see what it looks like. I'm interested in what happens to this expression when the x values become large. Like we said, n has to go to infinity. So I'm going to use the table feature. Right now, I go to second graph. It shows me a table of values for this expression starting with 1 and going up by 0.01. So if x is 1, I'm going to get 2. If x is 1.01, I'm going to get that other number, and so on. I want x to get really large because I'm trying to see what happens when it goes to infinity. So I'm going to do second window. And it says, where do you want the table to start? I'm going to say start the table at like 900. I want it to be large. And the change in the table, I don't want it to go up by 0.01, I want it to go up by 1. So I want to see what happens when it's like 901, 902, 903, and I want it to happen automatically, so I leave the auto buttons there. Then I go back to second graph, and now notice my table starts at 900, and when x is 900, I get something close to 2.71. Now let's go back to what I said. I said this approaches the number e. Right now, if n is, based on our table, if n is like 900, and I put 900 in there, that's what my calculator has done. If you punch that in, you'll see that that's going to be 2.7168. Now I want n to go to infinity, so even larger. So let's say now I go to like second window, and I say, hey, start my n at 1500 and then go up by 1. Second graph. And notice the number gets closer to e. Now it's 2.717, blah, 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 blah. Let's say I go to second window and I put like 2500 for my n value. Second graph. And now, when 2500 is input, I'm getting even closer to 2.718. In other words, you get the idea. The bigger n gets, the closer I'm going to get to e. So for now, we're just going to say, as n goes to infinity, this expression, 1 plus 1 over n to the n, is going to go and get closer and closer to the number e. Again, this is something you'll study in detail in calculus. For right now, all we're doing is just looking at a table of values and seeing that, hey, the bigger the input gets, the output gets closer and closer to the number e. Now, e basically, as far as you're concerned, is approximately 2.712, let's say. And if I want to look at the graph of the function, well, since e is between 2 and 3, your graph is going to look a lot like the graph of a function between 2 to the x and e to the x. So we know what 2 to the x looks like. We know what 3 to the x looks like. E is in between those guys. So basically, since the base is bigger than 1, it's a growth. And it essentially goes through 0, 1, like all the other ones do, and has a growth. So there is e to the x, a basic exponential function that would be in between 2 to the x and 3 to the x. You can also go on your graph and do second ln to get access to e, and then push x. So now I'm looking at e to the x, and if I do a zoom 6, it's going to give me the graph of e to the x. Notice again, it looks like it's touching the x-axis on the left. We know it is not because it has a horizontal asymptote. So let's point that out on the graph as well. Horizontal asymptote, just like all the other exponentials at y equals 0. One more thing, if you're on the regular screen on your TI, you could do second ln and put a 1 for your exponent and push enter, and it tells you some digits for the number e. The domain and the range. Well, we said all exponentials have domain negative infinity to positive infinity, and the range clearly starts at 0, not including 0, and goes off to infinity, just like your basic 2 to the x that we graphed in the previous sections. And as usual, we can apply transformations to the function and get other graphs. For example, the one right here has a vertical stretch by a factor of 3, and also it's shifted down 1 unit. So if I were to sketch that, my basic e to the x would look like that, going through 0, 1. Then it got stretched, so it kind of looks taller. And then when it goes down 1, that's when so the y-intercept of 0, 1 goes down 1, and along with it will also move down. Remember the horizontal asymptote, so now our horizontal asymptote is at y equals -1. So all transformations that we did before, pretty much the same idea applies to the function e to the x. Sketching it on your TI, graphing it on your TI, or sketching it by hand shouldn't be a whole lot different than what we've discussed before. Now let's go back and revisit the compound interest formula that we saw in the previous section. Now we want to look at this and see what happens if we increase the number of compounds per year in this compound interest formula. In the previous section, we looked at different n values. For example, we know that if n was equal to 12, interest was applied monthly to your account. If we increase that and let n be 365, that's going to be interest applied at the end of every day. And if we were to increase that even more, we would have n being 525,600. That should be a 600 for interest applied every minute, and we would have over 31 million for n if we were to apply interest every second, for example. Now, the idea here is, again, that we're increasing n in that formula, making it become bigger and bigger. So let's look at an example, kind of related to that problem. Say you invest only $1 at 100% interest rate for 1 year. Obviously, you're not going to find that anywhere, but nobody's going to double your money. But let's just look at what will happen to your money if it's compounded as follows: 1 time a year, twice a year, quarterly, or if n gets really, really big. So I'm going to use the compound interest formula. My principal is 1. 1 plus the interest rate is 100%, which means 1.00 in decimal form. So I have 1 over, and if n is 1, then I put 1 in my formula, and n times t, remember t is 1, and that's your p. So n is 1 and t is 1. I'm going to have 1 times 1 for my exponent. So basically what I have is 1 times 1 plus 1, which is just 1 times 2, which is $2. Which makes sense, because if you're going to get 100% of what you input at the end of the year when they apply the interest, your $1 is going to get doubled, and it's going to become $2. Now, what happens if interest is applied twice a year? In other words, it's happening semi-annually. So I'm putting in the dollar, and I have 1 plus 1 over, now n is 2, and I have nt, n is 2, time is still the 1 year, because you're only putting in your money for that 1 year, and that's going to be 1 times, I guess, 1.5 raised to the second, and that's going to give me 2.25. So if interest is applied semi-annually, meaning twice a year, your $1 is actually going to get not only doubled, but you're going to get a quarter more. And if you're not using the formula and just think it through, you have $1, and if you get interest on it, you get interest on that 100% interest is applied twice a year, you'll get 50% of that dollar at the end of 6 months, which will give you 1.5. So that happens at the end of 6 months. So at the end of 6 months, you'll have 1.5, and then your 1.5 will grow again by another 50% because you're doing the 100% twice a year. So the 1.5 that you had made is going to gain another 50% of itself, and that's going to end up giving you 2.25. Same thing that you would get if you just punched it into the compound interest formula. So if the interest is applied just once a year, you're going to have $2. If they apply the interest twice a year, you're going to have a quarter more, because again, your money is going to grow after 6 months, and then that growth money is going to get more money on top of it, and going to end up at $2.25. Now, what if it happens 4 times a year? So you have your $1 in principal, and then 1 plus 1 over n in this case is 4, and then nt, n is 4, t is still 1. So that's going to give us 1.25 raised to the 4th when we do the math, and that's going to give us about $2.44. So if they apply interest 4 times a year, you're actually going to get $2.44, because at the end of 3 months, they're going to apply interest, and your money is going to grow a little bit. Then at the end of the next 3 months, they're going to apply interest again, so your money is going to grow a little bit more, and they're going to keep doing that 4 times. In other words, the more compounds per year, I guess, we'll say, the more you're going to make money. Now, is your money going to go and become infinite if n gets really large? Well, it doesn't look like it, because A equals P is still $1. If I have 1 plus 1 over n, the number of compounds per year, I'm going to leave it as is, raised to the n times t, t is 1 year. Notice that's just going to give me that expression that we looked at the very beginning of the lesson. And so if n goes to infinity, using our calculator, we showed that this guy goes to e, which we said is approximately 2.72. In other words, even if it's compounded over and over and over, like 365 or every second or every minute, if your money grows, eventually you're just going to get $2.72. You're not going to make your money grow and bigger because you're just looking at that 1 year, and the number of compounds are increasing and becoming bigger and bigger. So we'll say even if compounded what's called continuously, our $1 becomes about $2.72 in that 1 year that you're putting your money in. But the idea is that the more times you compound, the bigger your money gets, from once a year to twice a year to 4 times a year and so forth. So we went ahead and already talked about this. Now let's see how compounding continuously will change our formula from what it was for quarterly, monthly, and so forth to letting n become bigger and bigger. So we'll start